Hello Advanced Physics, this is Dr. Brenzi and this is lesson 8.2.4. Our objective for this lesson is that we're going to be able to describe the relationship between voltage, current, and resistance in a circuit. Well, let's talk about a basic circuit. So when you see a diagram on a piece of paper like this, there are a couple of very key components here. First of all, at the very top there, we have a battery. You can think of this as a battery, like a battery you put in your remote control or a battery that you have in your car. It provides an electric potential. Okay, and I think I talked about this in the last lesson, but that electric potential is the same as the voltage of the battery. We also have a current that flows from the positive to the negative terminal. And one of the things that we have to be careful about is that the flow of the current is actually not the same as the flow of electrons. So we have to be careful and remember that electrons do the moving, and they do the moving in the opposite direction of the current. So electrons are actually moving from the negative and they're actually coming over here to the positive. And in reality, that's what's doing the moving, not any sort of positive charge. Right. The other thing that we have in here is this little squiggly line. And this squiggly line is what's called a resistor. And its job is to actually resist the current flowing from this positive charge or terminal over to the negative terminal. And if we don't have something that resists that current, then what happens is we end up doing what's called short-circuiting the battery. We produce a lot of current that flows through from here to here, and that causes bad things to happen to the battery, like the battery heats up and then it corrodes and nasty things happen. So you always want something that actually resists the flow of the current. And we call that a resistor. So there are some basic circuit rules that we generally follow when we're talking about ideal currents. And in a circuit diagram, you typically say that ideal wires have zero resistance. And compared to anything else that you see in this, like the resistor, compared to the resistance of the wires themselves is actually very, very small. Especially if we're talking about short lengths like a meter or half a meter. Really, you don't have to start considering the resistance of a wire until you get to very long distances, like you're talking about telephone lines or you're talking about power lines. So, for most ordinary circuits, we don't even need to worry about that, and we just say that wires have zero resistance. The second rule about circuits is that the voltage everywhere on a continuous piece of wire is constant. So if I say that this positive terminal is at a voltage or an electric potential of 1.5 volts, then every piece of point on this wire from here over to here also has an electric potential of 1.5 volts. On the other side of this battery, we have a voltage of 0 volts, which means that every one of these points from here all the way over to here has also a voltage of 0 volts. And the third rule of circuits that I want to tell you about now is that current only flows when you have a closed circuit. So we have a wire that runs from the positive terminal through a resistor over the negative terminal, and this would be considered a closed circuit. But if we were to cut the cord, cut the wire, we have an open circuit, and in that open circuit we have no current flowing. Okay, another very important law in circuits is what's called Ohm's Law. And Ohm's law states that the electric potential across a resistor, the change in electric potential, across this resistor is equal to the amount of current flowing through it times its resistance. So this is the way that we usually write. This is usually the way you'll see Ohm's law written, but I actually like to add a delta in front of here to remind myself that the electric potential here is different than the electric potential on the other side of the resistor. So it's actually a change in electric potential. Unfortunately, you don't see a lot of people writing it that way, but that's the way I think about it. And that's exactly what Ohm's law really means. So if I have a battery, and this positive terminal is at positive 1.5 volts electric potential, I use one of my rules of circuits to remind myself that that also means that this point is at 1.5 volts. The negative terminal is at 0 volts, so I also know that this point is at 0 volts. So this minus this will give me my change in electric potential. So that's 1.5 minus 0, which is 1.5 volts. And that is going to equal the current flowing through that resistor times the resistance of the resistor. So let's say we have a resistor whose resistance is 100 ohms. So if I write the other side of Ohm's law, I have 1.5, this is the change in voltage across the resistor, equals current times 100. And if I solve that for I am going to get 0.015 amps. So that's how much current is flowing through this resistor. And because that current is constant throughout the closed loop, that current is 0.015 amps throughout this entire circuit. So really it's the amount of resistance in this resistor that determines how much current is flowing through this wire. Okay, now things get interesting when you add more than one resistor to a circuit, and we call this arrangement a set of resistors in series. So when you have resistors that are on the same closed loop, we say that they are connected in series. Now there are two rules about having resistors connected in series, and the first one is that the current flowing through resistor 1 is the same as the current flowing through resistor 2, and we can just call that the current. So I have some sort of current, don't know what that is yet, and I have equal amount of current flowing through both of these resistors. By the way, I know my example already calls this top resistor R2. That's the way I did my example here, so I better change that real quickly, and I better change this to R1. Otherwise there's going to be some confusion. So the other thing I want to point out to you about this diagram is that this battery up here, in circuit diagrams, a symbol for a battery is a long line, small line, long line, small line. And the long line designates the positive end of the positive terminal of the battery. And this small line designates the negative side of the battery. Now sometimes you'll also see just two unequal lines instead of four. That is also a battery, and they just decide to be a little bit lazy. But it's perfectly acceptable, and everybody knows what it means. All right, so getting back to our circuit here. The change in voltage across resistor number 1 plus the change in voltage across resistor number 2 is equal to the voltage of the battery. So if I were to measure the change in potential from here to here, and measure the change in electric potential from here to here. And if I were to add those two together, I would get the voltage of this battery right here. So let's actually go through analyzing an example circuit when we have more than one resistor. So the first thing that I do, I better do this first. I better actually number these the way that I did my example. R2 and R1. Okay, yeah, that looks like a 2. So I'm going to write Ohm's Law for each of these resistors. So let's write out, oops, forgot about that. Forgot to tell you that the battery is a 12-volt battery. That's part of my example here. So let's write Ohm's Law for each resistor. So I have delta V1, that's down here. That is equal to the current flowing through this resistor times 100. And delta V2 is the current flowing through this resistor times 50 ohms. And you'll notice I already actually remembered the fact that the current flowing through two resistors in series is going to be the same, so I don't need to actually make an I1 and an I2. Those are just going to be the same number. So I just call that I. Now I use this fact that the change in voltage across resistor 1 plus the change across resistor 2 is equal to the voltage of the battery. And I am going to replace this V1 with this right here. I'm going to replace V2 with this over here. And the result is that I get this. 100I plus 50I equals 12, because 12 is the voltage of my battery. Now I can go ahead and use this fact to find the current. So I can combine like terms on the left-hand side, and I get 150I equals 12, and then of course I divide by 150, and I get 0.08 amps. So the current flowing throughout this entire circuit is 0.08 amps. Now I can use that fact to find delta V1 and delta V2. So I'm going to plug those back into up here. Right. Now I'm going to draw my current here first. Now let's go ahead and find that. So current, resistance equals change in voltage. So the change in voltage across resistor 1 is 8 volts. I know that this is at 12 volts because that is a continuous piece of wire from up here at the battery terminal. So I can also say that this is at 12 volts, which means that the other side of the resistor, I have to be at 12 minus 8, because this is 8, the drop, the change in voltage. So 12 minus 8 is equal to 4 volts. So that means that this little piece of wire is at an electric potential of 4 volts. And if I find delta V2, that's 0.08 times 50, and that's equal to 4 volts. So if I go from here over to there, I start off at 4 volts, and on the other side I get 4 minus 4 equals 0 volts. Well, that's a good check, because this is a continuous piece of wire from here to the negative terminal, so if the negative terminal is at 0 volts, I darn well better have this point be at 0 volts as well. So that serves as an awesome check. So that is how you analyze a series circuit. I now know the current flowing in through here. I now know the amount of electric potential that drops from here to here, and the amount of electric potential that drops from here to here, or the amount of voltage that drops from here to here. Okay, we're going to have an opportunity to practice that tomorrow in class and learn more about Ohm's Law and put it to use. And I look forward to seeing you then. Bye.